Welcome to this explainer on CompTIA Security Plus Objective 1.4. Today, we're going to explore exactly how digital trust is established online using cryptographic solutions. In a world where our data is constantly zipping around the globe, knowing how to securely prove who we actually are is pretty much the only thing standing between our private data and total chaos. Let's get into it.
So, here's our roadmap for today. We'll start with the foundations of digital trust, move on to blockchain and the decentralized ledger, then dive into certificates, which act as your digital passport. After that, we'll look at managing the certificate lifecycle and wrap things up with certificate formats and architectures.
All right, Section 1, Foundations of Digital Trust.
To solve the core problem of the internet, which is proving who we are and stopping people from faking data, we basically have two main approaches. We've got decentralized trust and centralized trust. On one hand, decentralized trust creates a system where there's absolutely no central authority. Instead, a ledger of truth is shared and verified by everyone in the network. On the other hand, centralized trust leans heavily on a neutral, trusted third party, like a bank or a certificate authority, to vouch for the identities of the people or the servers involved in a transaction.
Let's start with the first one. Section 2, Blockchain, the decentralized ledger.
So, a blockchain is essentially a database that gets duplicated across multiple participants. This is a concept known as distributed ledger technology, or DLT. Unlike a regular, traditional database, as new data comes in, it fills up a fresh block. Once that block is full, it gets chained chronologically to the previous one. The result? You get a historical record that is incredibly difficult, if not literally impossible, to secretly alter, hack, or cheat.
The really crucial point here is how this system actively prevents cheating. The open public ledger verifies account authenticity and checks if funds are actually available before a transaction goes through, which completely eliminates double buying. Because there's no central authority in charge, if someone tries to forge their personal ledger, the collective network instantly spots the fake and rejects that falsified data. Basically, you have to participate and donate computing power to the collective to use it, ensuring that everyone holds a piece of the truth.
Now let's flip over to the centralized model. Section 3, Certificates, your digital passport.
It helps to think of a certificate exactly like a digital passport. When you connect to a secure website, let's say PayPal, you and the website need to communicate safely. So a certificate authority, or CA, serves as a neutral third party negotiating the security between you and that site. They issue an electronic document that verifies the identity of the certificate holder, providing undeniable proof of their legitimacy right to your web browser.
But you can't just print your own passport, right? You have to apply for it. In the digital world, this is done by initiating a certificate signing request, or CSR. The requesting computer presents two absolutely critical items: proof of the user's identity and their public key. It's essentially a formal application saying, hey, here are my credentials and here's my public key. Please prove it's really me. The CA then compares this against their own private key, and if everything lines up, that trusted certificate is granted.
Certificates aren't all created equal, though. They're issued based on strict vetting levels. Domain validation, or DV, is the most basic. The CA just checks that the applicant actually has the right to use that specific domain name. Step up a level to organizational validation, or OV, and the CA conducts basic vetting of the actual organization behind the domain. Then, for the absolute highest level of trust, we have extended validation, or EV. Think of EV as the VIP background check of the internet. It requires the CA to conduct highly rigorous, thorough vetting of the organization before they'll hand over the certificate.
Now consider a self-signed certificate. It's much like a person who notarizes their own document instead of having it signed by an official notary public. It acts as both the creator and the endorser, signing with its own private key. Because it completely lacks that trusted external third party, it lacks broader public trust. And this is exactly why, when you visit a site using one, your browser will immediately throw up a giant warning flag. They're totally fine for internal testing, but you definitely don't want to use them for widespread public interaction.
Let's map out the chain of trust and see how validation builds organically from the bottom up. Down at the very bottom is your machine's end entity certificate. That's the one you actually see in your browser details. Moving up, that certificate handshakes with an intermediate CA certificate, which signs it. Finally, that intermediate certificate handshakes with the ultimate anchor at the very top, the root CA certificate. The root CA is self-signing, meaning it uses its own private key and code signing to provide the ultimate integrity and authenticity for the whole chain.
Because the root CA is the foundational element, if it gets compromised, it affects all downstream certificates. The entire chain of trust is completely broken. To prevent this kind of catastrophic failure, organizations treat these things like a spy movie. They utilize an offline root CA. By severing all network connections, this vault-like setup becomes impervious to remote network attacks. Certificates are then physically transported to the subordinate online CAs using removable media, like USB flash drives, all combined with super strict data loss prevention policies.
Section 4. Managing the certificate lifecycle. This brings us to a critical question. Certificates have a valid from and valid to date, sure, but what if a trusted entity is hacked or their private key is stolen today? We can't just sit around and wait for the certificate to expire naturally. We need immediate mechanisms to revoke their digital passport so users and browsers know instantly not to make unsafe connections. To handle this, we rely on two main methods. First, you can check revocation using a Certificate Revocation List, or CRL. This is a list digitally signed by the CA and published periodically, usually every 24 hours. It details certificates that are either irreversibly revoked or temporarily put on hold. Alternatively, systems can use the Online Certificate Status Protocol, or OSCP. As a trade-off, OSCP requires less overhead and is less complex for the client, but it lacks encryption, which actually makes the request itself slightly less secure than using a CRL.
Organizations also have to manage life cycles using some specific tools. First, there's Key Escrow, which securely archives a copy of a user's private key. This prevents catastrophic data loss if a key gets corrupted or if a third party like a government entity legally needs access. Then, on a Windows Enterprise CA, you can set up key recovery agents to restore any of those lost keys. Finally, from an efficiency standpoint, organizations often use wildcard certificates. These are the ones formatted like star.example.com. They allow a company to cost-effectively secure multiple subdomains with just a single certificate, rather than buying them all individually.
Section 5. Certificate Formats and Architectures.
Now, let's talk about how these certificates are actually encoded under the ITU-T X.690 standard. BER is the original rule set, and it allows for multiple encoding methods. CER tightens that up, restricting it to just one encoding type. But pay close attention to DER, the Distinguished Encoding Rules. DER is a highly restricted, strictly binary variant. It's widely used for X.509 certificates and is exclusively the format used for certificate enrollment in Windows servers.
Beyond the encoding itself, you'll encounter various file extensions out in the wild. PEM is incredibly common. It's a base 64 encoded ASCII format. Because it's readable human text, you can actually open it up in a standard text editor and clearly see the begin certificate and end certificate statements. On the other hand, PFX or P12 files are binary formats based on PKCS12. These are super useful because they bundle a server certificate, intermediate certificates, and the private key all into one single encryptable file, which Microsoft often uses for release signing. We can also contrast the standard centralized CA-based public key infrastructure we've been talking about with a decentralized model known as the Web of Trust. In a Web of Trust, there is no root CA. It's entirely peer-to-peer, operating with that same decentralized ethos as the blockchain we covered earlier. Users self-publish and attest to their own self-signed certificates, like you see in PGP. Users decide individually who to trust, and as they share those trusted certificates with others, the network grows organically. The more people who show trust in a particular certificate, the higher the chance it's actually legitimate. To further enhance certificate security beyond standard validation, there are a few best practices you really need to follow. First, you've got to move away from older hashes like MD5 and SHA-1. Implement powerful hashing algorithms like SHA-2 with your X.509 certificates. Furthermore, clients can use certificate pinning. This adds an extra validation step that checks the server's public key directly against a hashed public key tied to the server name right within a secure, up-to-date web browser. This is huge because it stops attackers who might try to secretly intercept your connection by slipping in a fake certificate. As we wrap up this explainer, I want to leave you with this thought. There have been so many certificate exploits in the past, and major vulnerabilities still exist today. Remember that whether you choose the decentralized, community-verified ledger of a blockchain or the strict, top-down hierarchy of a certificate authority, the safety of your digital communications depends entirely on how carefully you plan and implement these cryptographic solutions. Trust is the currency of the internet. Guard it wisely.